In Douglas Adams' book, The Hitchhiker's Guide to the Galaxy, a specially designed supercomputer, after 7.5 million years of continuous calculations, provided the answer to the ultimate question of life, the universe, and everything. And that answer turned out to be the number 42. If Douglas Adams were a physicist, it might have been a different number, most likely 137, or more precisely, the number 137, known as the fine structure constant, also called the Sommerfeld constant, or simply alpha. To be more precise, this value is equal to 7.297 multiplied by 10 to the power of 93, or approximately 1 divided by 137.035. This number, I believe, is known to every theoretical physicist and remains one of the most intriguing mysteries in quantum physics, specifically quantum electrodynamics. Although the concept of the fine structure constant became known to physicists in the early days of quantum mechanics. I am confident that no respectable science popularization channel can do without a video on the mystery of the fine structure constant, and that is precisely what we will delve into in our video today. So, sit back, make yourself comfortable, don't forget to subscribe to the channel if you haven't already done so, and let's explore one of the most intriguing mysteries of our universe. Early quantum mechanics primarily focused on understanding the structure of atoms and how their various components interacted. Since atoms are very small objects, and their nuclei and electrons even smaller, it was not so easy for physicists, especially in the late 19th and early 20th centuries, to learn something about them. One of the most observable phenomena, which could reveal some regularities and principles governing their behavior, was the absorption and emission of electromagnetic radiation by atoms, especially visible light. For example, since the mid-19th century, it was known that atoms emit and absorb electromagnetic radiation in a rather peculiar way. The spectrum of an atom consists of a kind of fence of lines, dark on a bright background in the case of absorption spectra, when we talk about light passing through a substance, and bright on a dark background if we study the emission spectrum of the substance itself. How well a particular atomic model explained this spectrum's structure historically became a key way to test its closeness to reality. One of the most immediate tasks for the emerging quantum mechanics was to explain the spectra of the simplest atom, the hydrogen atom with one proton in the nucleus and one electron on the periphery. Fortunately, by that time, the emission and absorption spectra of hydrogen had already been quite well studied by the efforts of many experimenters. Danish physicist Niels Bohr was the first to create a model of the hydrogen atom that theoretically explained the experimentally observed spectra. Following in the footsteps of his mentor, Ernest Rutherford, Bohr suggested that electrons orbit the nucleus, similar to planets orbiting the sun, and on each orbit, the kinetic energy of the electron should be equal to the potential energy of its electrical attraction to the nucleus. However, unlike Rutherford, Bohr supplemented the model with an assumption initially unrelated. Electrons in an atom can only have orbits, the angular momentum of which is an integer multiple of Planck's constant. From these assumptions, Bohr derived a formula that allowed constructing a kind of map of possible electron orbits around the nucleus of a hydrogen atom. Each of them corresponded to a specific value of the kinetic energy that the electron possessed on that orbit, or, as physicists prefer to say today, at a particular energy level. Accordingly, the linear character of absorption and emission spectra of atoms, and specifically the hydrogen atom, received a simple and elegant explanation. Hydrogen absorbs light only of certain wavelengths because photons corresponding to these wavelengths have the energy necessary and sufficient for an electron to transition from one energy level to another. Consequently, when we illuminate a substance with light consisting of photons of various energies, only those whose energy corresponds to one or another transition are absorbed, reducing the number of such photons in the spectrum passing through the substance, i.e., the absorption spectrum. When an electron transitions from a higher energy level to a lower one, it emits a photon whose energy corresponds to that transition, and the corresponding wavelengths appear in the emission spectrum. So here it is, the map of energy levels of the hydrogen atom, theoretically constructed by Bohr and his colleagues, corresponded quite well to the real spectra of hydrogen. The theory, as we discussed earlier, was quite naive from a modern point of view. For instance, today, we don't believe that electrons in an atom orbit in specific orbits. However, there was a grain of truth in the model, and it became the seed from which modern quantum physics grew. However, scientists soon managed to examine the spectral lines of hydrogen in more detail and found that each spectral line actually consists of lines with slightly different wavelengths, corresponding to energy levels with slightly different energies. For example, let's consider the so-called alpha line of the Lyman series in the hydrogen emission spectrum, also known as the Lyman alpha line. It corresponds to the electron transition in the atom from level 2 to the first energy level, i.e., the ground state. The energy difference between these levels is approximately 10 electron volts, and during the transition, a photon with a wavelength of about 120.567 nanometers is emitted. Well, it turned out that the Lyman alpha line is actually composed of two lines with wavelengths of 121.568 and 121.574 nanometers. In other words, the Lyman alpha line seems to split into two very closely spaced but still distinguishable lines, each corresponding to transitions to the ground state from two slightly different energy levels. This phenomenon was called the fine splitting of energy levels, and the hidden structure of spectral lines was termed their fine structure. The fine structure was also identified in other spectral lines of the hydrogen atom, as well as in the spectral lines of other atoms. Today, we know that the presence of fine structure in atomic spectra is explained by the so-called spin-orbit interaction. To avoid delving into quantum mechanical intricacies, let's explain it within the framework of the same naive but visually illustrative Bohr model, where the electron orbits around the nucleus. However, this time, let's consider everything from the viewpoint, or more precisely, from the reference frame of the electron itself, in which it is stationary, and the positively charged nucleus revolves around it, creating a magnetic field due to this rotation. In this reference frame, the electron is stationary, and therefore, this magnetic field seemingly should not affect it. After all, as we know, a magnetic field only acts on moving particles. However, even a stationary electron still has its own magnetic moment associated with one of its characteristics, known as spin. We discussed spin in one of our previous videos in more detail. So, possessing spin and thus its own magnetic moment, acting like a tiny magnet, the electron will respond to the magnetic field that arises in its own reference frame. Therefore, in addition to the potential energy of the purely electrical interaction between the electron and the nucleus, there will be some potential energy due to the interaction with the magnetic field. It turns out that the total potential energy of the electron in such a system will be slightly higher if its magnetic moment is directed in the same direction as the magnetic field resulting from its orbital motion, and slightly lower if they are directed in opposite directions. In other words, if we close our eyes to spin-orbit magnetic interaction, we will have one single energy level. But if we take this interaction into account, we will get two energy levels, slightly higher and slightly lower than the ground state. During the times we are talking about, the concept of spin had not been thought out yet. It was introduced into science in 1925 by Gaudsmit and Uhlenbeck, and physicists at that time could not theoretically explain, let alone calculate, spin-orbit interaction. Nevertheless, in 1916, Arnold Sommerfeld presented his formula for the quantitative calculation of the fine splitting magnitude, which yielded results that matched fairly well with experiments. Among other things, the magnitude of fine splitting turned out to be proportional to the square of a value equal to the square of the electron charge divided by the product of Planck's constant and the speed of light. This ultimately gives us 7.29710 to the power of -3, or approximately 1/137. Sommerfeld denoted this constant as alpha, and today we call it the fine structure constant, or Sommerfeld's constant, in his honor. If we delve into more detail, Sommerfeld derived his expression for the fine structure constant in the CGS system of units. In the more commonly used SI system, the expression would look like this. Let's emphasize, Sommerfeld essentially derived the correct formula without having an understanding of the true physical nature of the effect. Moreover, he made an error in the derivation of his formula, and due to this mistake, the incorrectly derived formula turned out to be accidentally correct, a case where a negative times a negative gives a positive. Such historical anecdotes do happen in physics. Much later, in 1928, Paul Dirac derived the correct formula for the magnitude of fine structure splitting from correct physical considerations. In this formula, the alpha constant was also present. The appearance of certain constants or coefficients in various physical formulas, especially if they are not fundamental constants but combinations of other quantities, is not surprising. In nuclear physics, there are numerous such constants: the Bohr magneton, Bohr radius, proton charge radius, Rydberg constant, and so on. However, physicists increasingly realized that there was something special about the Sommerfeld constant, and it meant something very important. Firstly, it was later discovered that this constant appears in many other formulas describing processes occurring in the atom. For instance, it was found that the kinetic energy of an electron in the hydrogen atom in its ground state is equal to its rest mass multiplied by the square of the speed of light, multiplied by the square of alpha. Furthermore, the electron charge was found to be exactly the square root of alpha times less than the so-called Planck charge, a value constructed from fundamental physical constants such as Planck's constant and the speed of light. However, the most astonishing aspect was that the fine structure constant turned out to be dimensionless. Indeed, if we substitute the dimensionalities of all physical quantities involved in its formula, we observe that all these dimensions cancel out. In other words, we obtain a dimensionless quantity, not just a quantity, but simply a number. This number, as we have seen before, mysteriously influences many parameters of what happens with the electron in an atom. What makes this unusual? Well, practically all physical constants have dimensions, and moreover, their dimensions, i.e. the units in which we measure them, directly determine their values. Take, for example, such a fundamental constant as the speed of light in a vacuum, which is 299,792.58 meters per second. We are accustomed to this particular value, but its magnitude could be entirely different. For instance, in kilometers per hour, it would be 1,079,000,000, in miles per hour, 670 million, and 616,000, in parsecs per year, 0.3, and so forth. We can even introduce a unit system where the speed of light is strictly 1, such as in the Planck unit system, which we discuss in a separate video. The same applies to other physical constants. In other words, the values of fundamental physical constants are, for the most part, the result of our agreements on the units in which we express them. With the alpha constant, it's not the same. No matter what unit system we choose, the fine structure constant will still be approximately 1/137. Furthermore, if we encounter extraterrestrial beings someday, their quantum physicists will also know about the number 137. Regardless of the units in which they express physical quantities. In principle, there are other dimensionless constants known to us, such as pi and e. However, they entered physics from mathematics. This is not the case with the fine structure constant, or, more accurately, the alpha constant. We observed this value directly from the universe, and it would be extremely interesting to find out what it truly signifies. This is one of the greatest damned mysteries of physics, a magical number given to us that humans don't understand at all. One could say that this number was written by the hand of God, and we do not know what moved his pencil, remarked Richard Feynman on this matter. While Wolfgang Pauli even said that the first question he would ask the devil when he goes to the other side would be about the meaning of the fine structure constant. Many physicists at various times attempted to answer the fundamental question of where the Sommerfeld constant comes from in a profound sense and why it has the specific value it does. For example, the renowned English astrophysicist Arthur Eddington spent many years working on this problem. In those times, around the late 1920s and early 1930s, the exact value of the fine structure constant had not yet been measured. Eddington developed a rather complex theory in which he argued that the quantity 1 divided by alpha represents the number of generalized degrees of freedom of the electron. He cleverly demonstrated that alpha should be equal to 1/136. Unfortunately, almost immediately after he published his calculations, new experiments showed that the value of alpha is closer to 137 than to 1/136. Eddington even built a new argument to show that it should be precisely this value. However, subsequent more accurate experiments demonstrated that the denominator of the fraction is not an integer, which definitively disproved Eddington's theories. According to modern understanding, the fine structure constant is a measure of the intensity of electromagnetic interaction, how actively a charged particle interacts with the electromagnetic field. I will try to illustrate this statement in a somewhat understandable way using relatively simple mathematics. The explanation will be somewhat imperfect from a strictly physical point of view, but I hope it will help viewers form an idea of what is meant. The force of electric repulsion between two stationary electrons at a distance r from each other is described by Coulomb's law. On the other hand, in quantum electrodynamics, their interaction is described by the exchange of a virtual photon. Roughly speaking, the right particle emits a photon with momentum p directed to the left, following the law of conservation of momentum, and starts moving to the right itself. When the photon reaches the left particle and is absorbed by it, its momentum is transferred to the second particle, causing it to move to the left. In other words, the observed electric repulsion. The force of such repulsion, according to a well-known mechanical relation, is equal to the transferred momentum, i.e., the photon's momentum, divided by the time of transfer of this momentum from one body to another. The momentum of the photon, as known, is equal to Planck's constant divided by the wavelength of the corresponding electromagnetic radiation. In our case, this wavelength will be equal to the distance between the particles. On the other hand, the interaction time, i.e., the time of photon propagation, will be equal to the distance between the particles divided by the speed of light. This leads us to the final expression for the force effect that would be equivalent to the exchange of electrons by a single photon with a wavelength equal to the distance between them. In other words, an individual portion of interaction in terms of quantum field theory. Comparing this expression for the zeroth order force of interaction with the expression for the total force given by Coulomb's law, we can easily see that the expression for the total force can be obtained from the expression for the zeroth order force by multiplying by the expression for our Sommerfeld constant, i.e., alpha. In other words, we arrive at such an expression from which the real physical meaning of the fine structure constant becomes understandable. It is the intensity with which electrons emit and absorb virtual photons, or, considering that the value of the fine structure constant is less than 1, it is more accurate to speak of the probability of an electron emitting and absorbing a virtual photon. Since the exchange of photons in quantum field theory is considered the mechanism of electromagnetic interaction, we conclude that the Sommerfeld constant plays the role of an indicator of the intensity of electromagnetic interaction in our universe. In this sense, the alpha constant does indeed play a fundamental role from a physical point of view, as electromagnetic interaction is one of the 4 fundamental interactions, meaning one of the 4 reasons why anything happens in the universe. In particular, the value of alpha determines which processes occur and which do not in nuclear and molecular physics and chemistry. If alpha were even a few percent greater or smaller than its current value, all these processes would occur quite differently, and, among other things, the existence of life as we know it would be impossible. However, this does not rule out the fact that in a universe with a different alpha, some other form of life could emerge, functioning according to completely different chemical or even physical laws. Similarly to the Sommerfeld constant, intensity indicators can be introduced for other fundamental interactions. For example, for strong nuclear interaction, the corresponding constant, according to modern measurements, is approximately 15, and for gravitational interaction, something on the order of 10 to the power of minus 39, which overall reflects our understanding of the strength ratio of these interactions. But why are these values exactly as they are? The only answer to this question that we currently have is that it is because the universe is structured this way. which, as regular viewers of my channel know, is a polite way of saying, we don't know this yet. Perhaps when a unified theory of fundamental interactions is created, we will get an answer to this question. Attempts to achieve this are currently being made in string theory, with the best result so far being 136.978. Not bad, but still not good enough. In connection with the problem of the fine structure constant's value, another question arises. Has this value always been like this in the past, and will it always remain like this in the future? Some physical theories suggest that the Sommerfeld constant could have had larger values in the early, denser, and hotter universe, and over time, as it expanded and cooled, decreased to the current values. Moreover, since the electron charge is involved in the value for the Sommerfeld constant, i.e., the charge of the smallest by mass, and therefore by rest energy, particle, it is believed that at the present moment, the fine structure constant has taken its minimum possible value and will not decrease further. That is, according to this theory, today we live in an era of the minimum possible intensity of electromagnetic interaction. Speculations about what the Sommerfeld constant was in the distant past of the universe are not entirely abstract. Thanks to the finite speed of light, we can literally look into the past by studying the light coming to us from distant galaxies, emitted billions of years ago. Indeed, if in those times when these remote objects emitted light that we see today, the fine structure constant had different values, i.e., electromagnetic interaction occurred differently, then the spectral lines that we find in this light should have looked different. Such studies have been conducted many times, starting from the 1960s and continuing to the present day. The latest such check, the information about which I was able to find, was conducted in 2020. By studying the light from a quasar emitted about 13 billion years ago, scientists found that the values of the fine structure constant in those times differed from what we measure today by no more than 0.002%. On the other hand, even in those distant times, the universe, in terms of densities of matter and energy, was already qualitatively similar to what we expect today, so it is premature to definitively conclude. We still cannot rule out that the fine structure constant had different values in the first minutes, hours, years, or even millennia of the universe's existence, but we have no evidence of this. Thus, although since the times of Bohr, Sommerfeld, Pauli, and Dirac, we have learned quite a lot about the fine structure constant, this number still hides a multitude of mysteries that future generations of physicists have yet to unravel. And this is great because the path of progress is nothing more than the path of sequentially solving these mysteries. And as long as we have questions without answers, we have room to grow. This means that in the future, science will be able to uncover new secrets of the universe, which, among other things, may form the basis for some new technologies that can change our daily lives for the better. In our upcoming videos, we will continue to explore both the already solved and the remaining mysteries of the universe. But for now, all the best, and until our next meeting.